Hi, how are you? Welcome to the Time Card Flex project. It is a PTP gateware. It's capable of Grandmaster Clock operation and based on this OCP-TAP Time Card. And this project is funded by AONET and NGI0. So I'll introduce the uh, usage of this time card, like how to build the firmware and how to do all the test, like hopefully in only one video. Then let's begin. Yeah, this is the README file in the uh, doc folder of this project. And laterally, I'm just demonstrating everything shown here. Like the card itself will be looking like this. And see, this is a OCXO 10 megahertz oscillator. It's mostly for a clock stable clock source during holdover. And this is the ZF9T GPS module. This is the antenna, and it's using a A-Link's Arctic 7 FPGA system on module. And there are quite some spare parts. It's quite over-engineered, and it's like uh, enough as a PTP Grandmaster Clock. And I'll just like show everything. First, I'll clone this project and build it. We'll be using this no vendor IP release, so everything is open source. There's no proprietary Xilinx IPs. I'm using Axie interconnect from Zip CPU, and the PCIe cores and like UART drivers are written by me. The main PTP functional IP cores are by NetTime Logic. You can just create this project, and this TCL script will also build the bitstream. So I'll just wait here. And now the bit stream has been generated, and we can use OpenFPGA loader to program this to the card. For the card is on the slot with a lot of SMA outputs on the computer, and on the leftmost FMC is connected to the GNSS pulse per second output, and then the third SMC is the PPS output from the time card itself. So like the GPS one is only available when the GNSS signal is up, and the time card one is always up. So like after I program bitstream, the two signal will be outputted on the scope. Now it's set to the scope is set to trigger mode. I see that after the initial configuration is done, we saw one signal per second. This is the PPS output from the time card. And since now the GPS cable is unplugged, there's no PPS from the GNSS model. And like to make PCIe be detected better, I will just reboot the machine with the card. You can see this PCIe device is connected, and we can load the driver. It's also in the repo, and we can just run this one to compile the kernel module. Well, as another test, if we don't want to use the module, we can just use a small script to test all the registers. Like now it's reading all F because the PCIe card is not enabled. We can enable it, and then it will like read all those information from the card, and then we can probe this kernel module, and in the log we can see like this PTP source is registered, and there are 0 ports like for GNSS output. We can like launch GPSD on this GNSS 0 port, and then run this CGPS to monitor this GPS interface. Like now there's no antenna, so of course it's not getting fixed. And now I will connect the GPS antenna. Now we see the PPI signal from GNSS is here, and actually this time card's PPI signal is being tuned to the GPS signal, and like it's an PID algorithm on the card to do this control. At most we can get is probably around plus minus 10 or 20 nanosecond, and as a test we can copy this time from the time card to the Linux system. We specified a 37-second time difference. This is the difference from UTC and the TAI on the satellites. And as a test, we can use NTP to sync the time. We can see the time difference is pretty small, and this is just the inaccuracy of NTP. So like now we know the time from this FPGA card is correct, and we can do a test like to sync time using PTP between this computer and a Raspberry Pi. So like for this, I've connected one channel to the PPS output from this Intel 210 Ethernet card PPS output, so I can compare the time delay between these two. And on the PC side, I will copy the time from this time cards PTP to this Ethernet cards PTP. And then I will launch the PTP Grandmaster Clock on this Ethernet card. And on the Raspberry Pi, I will launch the client for PTP. And we can see it can detect this master. And then I will turn on the PPS output from this Ethernet card. This is using the falling edge, so you can see like there's around half a microsecond difference, and is being stabilized here. So this is mainly the inaccuracy of copying the time from one card to the other, and to make the accuracy higher, we can use this TS to PHC to directly connect a output from the time card to the Ethernet card. And of course, for this, we will need an extra SMA connector outputting the PPS signal. So like on the first one. You can see like after using this scheme, now the time delay between the time card and this Raspberry Pi's Ethernet external Ethernet card is like 20 or less than 50 nanosecond. It is pretty good. And I can also like test another uh, recently released device, the Raspberry Pi Computing Module 5. This is a pretty new device, and there are some articles talking about it online, but generally, I'm gonna use a later kernel version to make it work according to the advices online. And there's a mistake on the silk string on the PCB. Uh, so the PPS output is actually uh, marked like USB OTG or whatever. This is the Raspberry Pi CM5, and it's the same. I just launched the PTP client. And I'll turn on this PPS output. So now it's stabilized and the server is like in a good configuration. But like there's still 200 nanosecond difference. Probably this is the performance limit of this BCM Ethernet PHY. But generally it's working, and 200 nanosecond is probably like not a big deal for most applications. And that's most of it about this time card and testing connections using it. And if you happen to uh, be playing with PTP, I hope this video can help you. Thank you for listening.